Welcome to Control Systems Lectures. We will now continue with our lecture on time response analysis, which is found in chapter 4 of your textbook. The underdamped second order system is one of the common models for physical systems, and hence it warrants a proper description for the purpose of analysis and design. Apart from the natural frequency omega subscript n and damping ratio zeta specifications, there are other peculiar specifications to this system that we need to consider. Our first goal is to define these transient response specifications. We will start by finding the step response for the generic second order system shown by equation 1, and then we will find the transform form assuming that zeta is less than 1. This implies that we are dealing with a complex conjugate solution case. Performing partial fraction expansion on equation 2 for the case of complex conjugate will yield equation 3. Taking the inverse Laplace transform of equation 3 will yield equation 4, where phi is tan inverse zeta over the square root of 1 minus zeta squared. When we plot equation 4 for different values of damping ratio zeta, we will get this figure. Note how the oscillation increases when the value of zeta is lower. In this plot, the x-axis is the normalized time using the natural frequency as a normalizing factor. It means that the natural frequency is only a scaling factor and will not affect the response in any other way than to scale it in time. Apart from the natural frequency and damping coefficient, we would like to introduce other specifications for the underdamped second order system. These are the rise time, which is the time required for the waveform to go from 0.1 to 0.9 of its final value. Then we have the peak time, which is the time it requires for the system's response to reach its first or maximum peak. And then we have percentage overshoot, which is the amount the waveform overshoots the steady state value. And then settling time, the time required for the transient damp oscillation to reach and stay within plus or minus 2% of the steady state value. All these specifications will be evaluated as functions of the natural frequency omega subscript n and damping ratio zeta. Note that it is not possible to obtain a precise analytical expression for the rise time, and hence a curve fitting method is employed. We define the peak time T subscript P as the time required to reach the first or maximum peak, starting from the response equation of a general second order system. We can find T subscript P by differentiating C in the time domain Ct, that is the response of the system, and equating it to 0. This will yield equation 5. For this equation to be 0, it means that the sign quantity must be 0, and this will occur when omega subscript n square root of 1 minus zeta squared t is equals to 0 or pi or 2 pi, because any of these quantity will give us sign of this quantity to be 0. Hence we can write t as shown in equation 6. So we now have the equation with respect to the time t. Each value of n in this equation will yield a maxima or minima. At n equals to 0, we get the first point on the curve with 0 slope. And then at n equals to 1, we have our first peak, which is T subscript P, which is then given by equation 7. We define the percentage overshoot as the amount that the waveform overshoots the steady state or final value at the peak time, expressed as the percentage of the steady state value. From the graph, we can see that it can be expressed by Cmax, or C subscript max minus C final divided by C final multiplied by 100, which is equation 8. C max is C of t at the peak time, Tp, which yields equation 9. For the unit step input, C final will have to be 1. Hence, if we substitute equation 9 and 10 into 8, we will get the expression for the percentage overshoot shown in equation 11. From equation 11, it shows that if we know the percentage overshoot, we can easily compute the value of zeta. So from 11, we can make zeta the subject of the formula, which will yield equation 12. You can verify this for yourself. From the definition of settling time, it means we need to find the time it takes the amplitude of the decaying sinusoid in equation 4 to reach 0.02. Therefore, we equate the amplitude to 0.02. Note that this is conservative because we are assuming that the cos component is 1 at the settling time. Hence, settling time will be given by equation 14. The value of the numerator of equation 14, log minus log 0.2 square root 1 minus zeta square, for values of zeta greater than or equals to 0 and zeta less than or equals to 0.9 yields values between 3.91 to 4.74. You can verify these by substituting the values of zeta in this range into this equation, and you will get that for each of these you will get the value between 3.91 to 4.74. Therefore, we approximate the numerator to be 4. Hence, we can write our settling time T subscript S to be equals to 4 over zeta omega subscript N. Now, let's look at the rise time. We define the rise time as the time required for the waveform to go from 0.1 to 0.9 of the final value. There is no precise relationship between rise time and the damping ratio. A curve fitting technique, however, is used. The curve is produced using equation 4 and the varying values of zeta. The time axis is normalized with the natural frequency. This curve can be approximated by the following polynomials. Maximum error is less than 0.5% for zeta values of lying between 0 and 0.9. And the second polynomial gives a maximum error of less than 5% for zeta lying between 0.1 and 0.9. That is, zeta is greater than 0.1 but less than 0.9. In this example, we are to find the peak time, the percentage overshoot, and the settling time, and the rise time from transfer function given this particular transfer function. Try solving this using all the equations we have derived, and you should get the following solutions. We will now relate the second order system specifications to the poles locations. Recall that we use the generalized second order system given by G of S to find the poles, which are the two poles S1, 2 equals to minus zeta omega subscript n plus or minus omega subscript n square root of zeta square minus 1 for zeta greater than 0 and less than 1. We now plot these poles on the S-plane, where omega subscript d is referred to as the damped frequency of oscillation, and zeta subscript d is the magnitude of the real part and is called the exponential damping frequency. Using Pythagorean theorem, we can see that the radial distance from the origin to the pole is the natural frequency omega subscript n. And the cosine of the angle theta, cos theta, is the damping coefficient. Let us relate the specifications to the poles. The peak time is given by equation 7 from the plot. This is pi divided by the imaginary component, where omega d, the damp frequency of oscillation. The settling time is given by equation 15, and it is 4 over the exponentially damping frequency, which is 4 divided by the real part. Equation 7 shows that the peak time is inversely proportional to the imaginary part of the pole. Therefore, horizontal lines are lines of constant peak time. Similarly, equation 15 shows that the settling time is inversely proportional to the real part of the pole. Since zeta is cos theta, radial lines are lines of constant zeta. And since percentage overshoot is a function of only zeta, it means that radial lines are lines of constant percentage overshoot. We will now use a step response to show how moving the poles influence the system. In figure A, we move the poles in the vertical direction while keeping the real part constant. As the pole moves vertically, the frequency increases. But since the real part is the same, the exponential envelope is the same. This implies that the settling time will be the same for all waveforms. Also note that as the overshoot increases, the rise time decreases. If we now move the poles horizontally, that is changing the real part but keeping the imaginary part the same, we have figure B. Note that as the pole moves to the left, the response damps quickly, but the frequency remains the same. Note that the peak time remains the same because the imaginary part is the same. And finally, if we move the poles along a constant radial line, we have figure C. Note that in this case, the percentage overshoot remains the same. Also notice that the responses looks exactly alike, except that the speed varies. The farther the poles are from the origin, the more rapid the response. Let us conclude this lecture with this example, which is found in page 184 of your textbook. Given the pole plot shown in this figure, we are to find the peak time, percentage overshoot, and the settling time from the pole locations. First, we need to find our zeta and our natural frequency omega subscript n. We have shown that the radial lines is omega subscript n. Therefore, we can easily find our omega subscript n using Pythagorean's theorem, which is equals to the square root of 7 squared plus 3 squared. This gives us 7.616. We can then compute zeta as cos theta, which is 3 over 7.616. This gives us 0.394. We can clearly see that this is a case of underdamped system. From here, we will just apply the equations for the specifications to find the desired quantities. Therefore, the peak time is pi over omega subscript d, which gives us pi over 7. This gives us 0.449 seconds. And the percentage overshoot is given by this equation, e raised to the power minus zeta pi over the square root 1 minus zeta square, substituting the value of zeta into this equation and multiplying everything by 100, we get percentage overshoot of 26%. Try solving some other questions at the end of this chapter in your textbook so that you are able to familiarize yourself with solving problems with these equations. Alright, this concludes our lecture on time response analysis. Since you are armed with this knowledge, you can apply it in subsequent topics as we progress in the course. Thank you.